Hello everyone, this is Group E. My name is Samuel Eastlick, and together with Chase Harwell and Lynn Komarick, we will be showing you Project Smart Mirror. The main goal of our project was to create a casual tool for home productivity. Everything is shown on the display that doubles as a mirror using two-way film. The idea is, as a user is getting ready for the day, they can see any important information at a glance. This display would show information such as current weather, upcoming calendar events using the built-in Google Calendar support, and simple media casting, such as YouTube videos for makeup tutorials, music, or anything in between. The mirror measures 22 inches diagonally, something still big enough to be used as a mirror and have plenty of space for the information being presented, while also remaining a reasonable cost for us students. All settings and features will be controlled using a smartphone app, preventing the need for an expensive touchscreen while also saving the display from being covered in fingerprints. The smartphone app connects over a lamp stack, and the mirror pulls data from a MySQL database. After the user has logged into their Google Calendar service, Spotify service, and provided their general location for weather services, the mirror will provide all other data at a glance.
The motivation behind Project Smart Mirror is that we wanted to take an ordinary piece found in almost every household and update it to make it more suitable for life in the 21st century. While we were adding these updated features, we also wanted the object to appear as though it had no smart features at all when it's not being actively used. We found that there are some smart mirrors on the market today, however, they either lack any customization whatsoever or they come with a hefty price tag. With Project Smart Mirror, we wanted to bring a decent level of customization at a minimal cost to the end user.
For our initial inspiration, we can look at existing products. Smart mirrors are on the rise and can be found anywhere from Amazon to Walmart, but are usually quite expensive. When considering our design, we picked features that we liked, for example, unobtrusive graphics, and combine all the features we enjoyed to make a mirror of our own. This process can help save us money and make the mirror more tailored to our own use case.
When designing this project, we had a few goals and objectives in mind. The first being that the mirror is to look like a simple mirror when the device is turned off. We wanted the smart mirror to blend in with its environment when it's not in use. This is why we elected to implement a one-way mirror overlay with the display. The next aspect of this project we thought about was the included features. We brainstormed about what information most people might want to see when they first get up in the morning. The first pieces of information would be the day's weather and events on a person's calendar. We also wanted to add more features such as alarm clock and media casting capabilities to make the mirror even more useful. We also decided that the mirror needed a frame. The best way to hide the internals and for the mirror to blend in as a decorative piece would be to add a frame rather than just having the mirror alone. Finally, we thought about functionality. We realized that most people would not want a touchscreen mirror because that would lead to fingerprints all over the place. This is why we decided to include a companion app in the project so that users can change settings and widget locations without actually having to touch the mirror.
The mirror is 22 inches diagonal. The white frame extends roughly 3 inches on the exterior. The front of the computer display is glued onto the back of a two-way mirror, making sure that the access ports are still there, which has input HDMI and USB. There's also some holes in the back to thread the power wire through. Hopefully it will fit flush against a wall, and it's still under 15 pounds without anything else added, but the PCB additions will be small and light, and the Raspberry Pi too, which we will get to soon. The chart here displays all of the engineering specifications we set for this project. The 3 highlighted ones will be shown in our project demo video. The Smart Mirror program itself should be able to boot up and load all the most recent data in under 5 seconds. And once booted up, the companion app should be able to connect to the mirror in under 3 seconds. Furthermore, every time an app update is made using the companion app, the Smart Mirror should take at the most 5 seconds to update the widgets with the new data. This is the overall block diagram for this project that highlights the responsibilities for each group member. Next, we will break down our major subsystems in this project. We will touch on the concept of having an Internet of Things device and using our display to control via an app that we create, and how our Raspberry Pi fits into all of this, while we break down some of the other internal pieces from the app and the PCB and all the decision making for what went on behind the scenes.
When it came to the development board for this project, we narrowed it down to two options, the Raspberry Pi 4 and the Arduino Uno. Both options are very popular development boards, but in the end, we elected to go with the Raspberry Pi 4 for a few reasons. The included connectivity of the Raspberry Pi was the main reason we chose this development board. It included Wi-Fi and Bluetooth modules, meant that we did not have to have separate controllers installed for any sort of wireless communication. Bluetooth will be used to play music on the mirror from a smartphone, and Wi-Fi will be used to fetch data from external sources. We also concluded that 2 kilobytes of RAM on the Arduino Uno would not be enough to run our graphical user interface, but the 2 gigabytes on the Raspberry Pi would be more than enough.
For our motion sensor, we had two technologies to choose from, an ultrasonic sensor and a standard CMOS camera sensor. Both technologies work in different ways to achieve the same end result. To get distance information, the ultrasonic sensor sends out a sound wave and waits for it to be reflected back to the onboard receiver. The distance is then calculated by measuring the amount of time it took for the sound wave to come back. CMOS sensors use light to obtain distance information. The sensor will collect various wavelengths of light present in the room and convert them into electrons that can be used in a circuit. The charges are then sent into an analog to digital converter where they are translated into pixel colors to form an image. There are two main choices we considered when thinking about motion sensing devices in our project. Simply put, the distance sensor would be more straightforward to implement. Our group already owns this part from junior design and is familiar with how it works. While the Kinect would offer more functionality in terms of gesture controls, we felt it would overcomplicate software development. In a perfect world, gesture controls make sense, but in practice they can feel more like a frustrating gimmick. So we chose the distance sensor. It will read a different value depending on when someone is standing in front of the mirror or not, and act accordingly to turn the screen on or off. Here are two microcontrollers we considered using. Put simply, we went for the MSP430 because it has a wider range for the operating voltage, it has better power consumption with the low power mode, and our group has plenty of experience developing the board. For our PCB design, we ultimately elected to use the MSP430 FR6989 microcontroller. We chose this MCU because we felt the most confident in our experience with this microcontroller. The MSP430 has been used in our junior design project, and we have also used it in our embedded systems course at UCF. The MCU in our project has very basic tasks. All it has to do is handle any physical input from the user. These inputs could include turning the volume dial or getting information from the motion sensor. When the MCU receives any outside data, it will either directly control a hardware component, like in the case of turning the volume dial up or down, or it will send data to the Raspberry Pi, like in the case of distance information from the distance sensor. The MSP430 will send this data to the Raspberry Pi using a common communication protocol, such as UART.
This is our PCB, which is basically just an audio amplifier. We can route all of the connections back to the Pi, and the Pi is the main control of the smart mirror. I used Easy EDA because I found JLC PCB can manufacture your board straight from those files. I know Eagle works just the same way with other manufacturers, but this was actually very basic, which I needed for my design. And our board has screw holes just in case we want to mount it either inside the actual mirror or maybe like on a little outside component box where we can adjust the potentiometers to do like brightness and audio. But we also have an audio jack to directly plug into your phone or into a possible Raspberry Pi. I like the idea of using potentiometers for turning up and down the audio controls because it reminds me of the radio dial in your car. But it's just as easy to press buttons like an up button or a down button. But we also use the potentiometer idea in junior design, so we were running with that too. PCB design was done on Easy EDA and ordered through JLC PCB. The main part of our circuit is an audio amplifier, and it is powered by the op-amp LM386N1. So our original smart mirror design did not include a plan for speakers, so our PCB would have to fill in the gaps because the Raspberry Pi does also not come with speakers. There are 3 potentiometers included in our design, one for volume and clarity and bass boost. The voltage is regulated through the circuit and can operate independently of the other sensors on the board. Some of the design challenges we encountered were connecting our PCB to a power supply. The original PCB design we had was connected to a 9-volt battery. We considered this option to be too difficult to change the battery when it dies because then you'd have to take your mirror off the wall and the music is on for quite a while, so the battery would die frequently. We connected the speaker to the GPIO pins on the Raspberry Pi, so the Raspberry Pi would constantly be connected while the mirror was connected to power in the wall. And we can successfully play music through the GPIO pins and the audio jack from the Pi to the audio jack on the PCB. Some other considerations we had when programming our PCB was how to get the code onto it. So we ended up using screw terminals to put jumpers in temporarily so we can plug the PCB into the computer to program using Code Composer Studio. Then we could communicate through the board, through the MSP430 chip, and using SPI or UART connection to read our temperatures from our humidity and motion sensors.
Moving on, we will talk about the application running on the mirror. Here are some concepts for the mirror's user interface. The main philosophy when coming up with this design was to keep the middle of the mirror mostly free of content. That way the mirror can still fulfill its main purpose without anything getting in the way of the user's reflection. As for where the time, weather, calendar, and media elements are all located, these can be rearranged based on the user's preferences in the settings. Chase will detail this later when going over the mobile companion app. Our team chose to use Python for our primary coding language. While Java and C are more well known by the team, we felt that Python was better suited for both the Raspbian operating system our app would live in and the data-centric nature of the app itself. We weren't totally familiar with Python at the beginning, but this turned out not to be an issue as it was truly easy to learn. Weather is one of our primary data points that we want to show our user. There are 2 options that we came across during research: RESTful API and Raspbian Weather Utility. RESTful quickly fetches weather information from a database of weather stations with 8 sensors available from each station. In order to find the closest station, the user's general longitude and latitude are needed, which is obviously not very user-friendly. Furthermore, some weather conditions, such as sky condition, aren't outright known and would need to be inferenced based on the 8 available sensors. Finally, RESTful does not offer any weather prediction. Raspbian Weather Utility, on the other hand, has fewer data points, but they prove to be better for our use case. More importantly, weather prediction is possible through the Weather Utility. In addition, there's a much more intuitive location service. The user can simply give either their zip code or city name instead of their coordinates. And while the Weather Utility does initially take longer to retrieve data, this can be brought up to a similar speed by saving the lookup information to be used again later. Initially, we were planning on using both tools to fetch the weather, but after consideration, it makes more sense just to solely use the Raspbian weather utility. For a calendar service, we considered Google Calendar and Microsoft Outlook. Both options are almost identical in terms of our use case, because both Google and Microsoft provide useful quick start examples for getting started using their service with Python. The steps are relatively the same and the end result would have been identical, so the choice came down to whatever our preference was. Since most of us already have a Google account, it made the most sense to integrate that into our app. For the user's calendar and event data, we chose to use Google Calendar. To start, the app must be authenticated and have a verified token, which is generated by Google. Google uses OAuth 2.0 and JSON Web Tokens for authentication. From there, the scope of information that will be used by the app must be documented so that the user can verify and accept what the app will have access to. When the user first signs in, they will be presented with this list and the request to give the app permission to access their account. You might be familiar with this process if you've ever signed into an app like Spotify using your Google account. Once authentication is complete, the data is available through several API endpoints with which calendars and events can be requested by the app. Once that data has been retrieved, it can be displayed in a number of ways according to the user's preferences defined in the settings. Possible layouts include daily events, weekly events, cycling through upcoming events, or displaying a full monthly calendar. Finally, on occasion, the service will request updates from Google to ensure that all data is up to date.
Now we will discuss the design of the Smart Mirror companion app. The main goal when designing the Smart Mirror companion app was to provide an easy and intuitive environment to interact with and change settings on the Smart Mirror. The two main functions of the app is to edit the layout of widgets on the mirror, along with changing settings of the mirror. Any changes made in the app will be sent over a local connection to the MySQL database on the Raspberry Pi. Then the main mirror program can grab those changes and implement them as needed. As stated earlier, the benefit of having a companion app with this project is that it eliminates the possibility of getting fingerprints on the screen just to move a few things around. Here is the final graphical user interface for the Smart Mirror companion app. The companion app could be developed using one of these three platforms: Xcode, React Native, or Flutter. All three of these development platforms use a different programming language. Xcode uses Swift, React Native uses JavaScript, and Flutter uses a language called Dart. Operating system compatibility was also something to take into consideration. Both React Native and Flutter can be developed on any platform and deployed to any OS. Xcode is developed by Apple, so Apple products are required for development and deployment. All three development platforms had some pros and cons that came with them. The benefits of using Xcode would be that I, as the main companion app developer, have the most experience using Swift and SwiftUI on Xcode, along with the fact that SwiftUI has a feature where developers can drag and drop elements onto a screen. Xcode would then automatically add the required code to the scenes file. This would save a lot of time on the UI development since placement would not have to be coded manually. However, using Xcode would mean that if I run into trouble, I am truly on my own. Since Xcode is a Mac exclusive and I am the only one with a Mac OS machine, I would not be able to get any help from the other developer on the team. The benefits of using React Native would mean that there is cross-platform development and deployment, meaning that both computer engineers on the team could work on the app if needed. However, React Native has been used in previous projects for other courses at UCF, and the experience was unpleasant. Deployment of the app to a physical device using Expo is also a negative aspect of React Native, in my opinion. Finally, there is Flutter. Flutter uses a programming language called Dart that has Java-like syntax. Both developers on the team are very comfortable with Java, so there should be a quick learning curve. However, it does mean that the developers of the companion app would have to essentially learn a new programming language for this project. We concluded that the pros outweighed the cons for Flutter, so we chose that as our companion app development platform. Here is a simple block diagram for the companion app. Upon startup, the app will check for a connection to the mirror using the local IP address. If a connection can be established, then the main screen is displayed for the user. If there is no connection to the mirror, then a no mirror connected screen will be shown until a connection can be established. Once the main screen has been reached, there will be two buttons to press, the Edit Layout button or the Settings button. If the Edit Layout button is clicked, the user will be sent to a new screen where they can swipe between all the possible layouts for mirror widgets. On the Settings screen, users can change the user or device name, change the location for weather services, sign in and out of Google, cast a video to the mirror, or change the timers that are currently active. During the development process of the companion app, it came to light that the Flutter libraries we planned to use for Bluetooth connectivity were not compatible with the iOS operating system. This was due to Apple's strict made-for-iPhone licensing program requirements, hindering development of any type of serial Bluetooth library in Flutter. Since Bluetooth was no longer an option for us, we had to go back to the drawing board to figure out how the settings were going to get passed from the mobile app to the mirror itself. We landed on a web stack, and more specifically, a LAMP stack. The MySQL database and the Apache web server could both be run locally on the Raspberry Pi Smart Mirror, so we did not have to worry about getting a third-party hosting service. To communicate with the database on the Pi, the mobile app will attempt to make a local connection on a home network and then call one of various API endpoints that we have created to update the data. These endpoints were coded in PHP. The main app will periodically refresh a JSON file with information gathered from the database and ensure the settings are changed with a decent response time. When we ran into the issue of needing to use a web stack to connect the mobile app and the smart mirror, we narrowed our decision down to two choices, a LAMP stack or a MERN stack. Both of these web stacks use databases that would be able to be accessed by a Raspberry Pi, so compatibility was not an issue. During our research, we discovered it is rather simple to create a MySQL database and also run an Apache web server on a Raspberry Pi. This meant that we would be able to store the data for our mirror settings locally on the Pi, rather than fetching it over the internet. With those things in mind, we settled on using a LAMP stack to replace our Bluetooth connectivity. For the work distribution, Chase and Sam were responsible for all things software. Sam was the lead developer of the Raspberry Pi app, and Chase was the leader of the companion app and stack development. Lynn was responsible for all things hardware and PCB related. Here's the final budget for our project. Our total MSRP for parts came out to be $454.25. However, our group was already in possession of the Raspberry Pi and the ultrasonic distance sensor, which brought our grand total to $402.70. Our original build estimate from Senior Design 1 was $360, so we were happy with the final price we paid for this smart mirror. Thank you for watching. We hope you enjoyed this presentation.